Few quick announcements. Homework 3 is due tonight. I think everyone knows that. It feels like a homework day in class. Finally, also, well, not finally for the second one, but we posted the Geographic Information Systems tutorial on the website. So you can look at that as an example of a tutorial and kind of what we're sort of looking for in that. I realized we haven't released yet the script that'll count the words and lines of code, but we'll release that too. It's just a little Python script you can run on your notebook. The other thing that actually I did want to point out, though, I'll try to actually, if I don't do this within the end of the week, someone remind me to do it. But the tutorials themselves, they should actually be readable without running the code itself. So someone should be able to run the code and download it if they want to. But if you look at the link on the tutorial on the website, I actually am linking to a static rendering of that notebook, and all the outputs are included and all the code's included. And hopefully, the idea being at least, that you can actually kind of read through it just as a static website. And that provides some value in addition to if you download it then and run it at all. The big advantage here is that if you have trouble installing library, if you write some tutorial and then someone else tries to run it and they have to, the person evaluating it, us and the other evaluators, if they try to run it and they can't install some library, you don't want to have them essentially not be able to do any of your tutorial because they can't run the code. So instead of doing that, make sure that your tutorial kind of can read like just a final, like a report essentially, right? You want it to be able to do that, and the one I've posted is a example of that. So kind of follow that mold. We may or may not link to the actual, it's called NB Viewer is the app for rendering them in a static page or not. We may do that. We might just distribute them as Python notebooks. But you should be able to load them and just immediately read the whole thing without running any code. So I'll add a note about that. Maybe actually a few notes about the tutorial in general. But that's one important mention. Yeah?
The tutorial should have like its marked down parts and then the code parts which are pre-written so that and commented, preferably so that people wouldn't have to run anything to see the outcome.
Correct. So yeah. So the question was, should everything be pre-run? But yes. So you should generate all the output that you have so that you can actually, someone reading it, just opening the notebook and reading through it with the markdown and with the code can just read it as kind of like a instructional book, as opposed to having to run it. They can run it if they want. That's the idea, right? Is that the nice thing about notebooks is you can download it and run it, but you don't have to. So I will clarify that on the website. If your midterm report is not of that character, don't worry, because we won't worry about that one. That's due next week. We won't. If you're kind of far along already, you don't have time to do that. That's fine. But the final report should be like that, and we'll post some clarifying information about that. And then the same goes for the final project reports too. That is actually mentioned in the final project report description that we have on the website now, but I realized I didn't specify that for the tutorial, so I want to emphasize that. So I'll post some more information about the tutorials in general. I think the current assignment was a little bit sparse, so we'll kind of elaborate on that. And then you can ask any follow-up questions on that over Piazza. Important dates for the final now. So for the final, we've made some switches on this for hopefully good reasons. The project report was, or the description of the project was released on Monday. Some important dates for that are the 24th, you have to submit proposals. We'll send out a link for a Google form to submit your proposals. Much like the tutorial, it'll be a form you have to fill out. But for that, you have to have already picked a group for it. So you need to pick your group, submit it and submit your group information. You have to also then submit a 200-word maximum description of your topic. So again, it's meant to be a quick check, not a justification of why you want to do it. Just describe what you want to do. And we can kind of hopefully get some feedback of this is good or this needs some focus. That's due the 24th. On the 11th, the midterm report will be due. There's the details about that in the write-up as well. For those first two, they don't count. They count a little bit towards your grade, but the main purpose there is just to make sure you do it. As long as you make a reasonable effort, where we determine what's reasonable, so I guess it's hard to define. But as long as you make a reasonable effort in our in our estimation, you'll get full credit for the proposal and for the midterm report. They're not meant to actually be evaluated. They're meant to kind of make sure you're hitting the milestones towards your final, which is going to be the majority of the report. The second thing is that we've moved the last 2 dates. So the final projects are now going to be due on the 9th, not the 7th. The 7th is the last day of class. And for the last day of class, I actually wanted people to be here, and I'm just positive no one would ever actually come if the final report was due that evening. So I will encourage people to come also separately to that lecture. And so I changed the final to be due on the Friday following it. It's the last day of classes. Not this class, but classes in general. And then the final presentations, which are going to be essentially you come to an auditorium, we play the videos people have submitted, and you will also evaluate some of the people's submissions, some subset of the people's submissions. Those evaluations you do are just for feedback. They're not going to count towards the other group's grade on the project. They're just sort of to provide feedback about that. And they're part, you get graded for doing them, not for your comments that you get. But then that will be on the 14th. The 14th is not our final date. It just seemed like, since we said there was no final, having a final date then on the 18th seemed a little bit cruel. So what we're going to do instead is we're going to have it on the 14th. But because we're having it during a period that's technically a reading day, it's not absolutely mandatory that you have to come. So we encourage everyone that is here, strongly encourage, if you can make it. It's not a final, so you don't have to really study for it. You just sit. I mean, you have to prepare your video for it, but you don't. Once you're there, you just watch. We would encourage everyone that can make it to please come. But if you can't, for some reason, if you have a final, early the next morning, we understand. We will also let you watch all the videos online, and then similarly write your descriptions there. The way we'll make sure that you watch them all is that we will not tell you where your projects that you're supposed to evaluate are in the middle of that, so you have to actually watch the thing. I guess you can skip around, but we'll try to watch them all. They're going to be really short, so 2 minutes each. So people presumably will put a fair amount of effort into those 2 minutes. Okay, so does that make sense? I'm just sort of all this should be described in much better language in the presentation or the project description, but let me know if there are any questions on that. One thing which I did not mention here is that we're going to have some extra office hours today for the homework. Divya will send out the time for that to post it to Piazza whenever we schedule that. Okay, questions? Yeah.
For the next month or two, there's a lot of deadlines and things due for this course. Will the homeworks be adjusted in length to compensate for it?
So the question was, will the homeworks be adjusted in length to compensate for that? There's two answers. The first one is that hopefully some of the homework stuff, a little bit, but maybe not as much as, okay. Two answers to that. The first answer is there was a Piazza post about this, so I'm going to address that as well. I responded to that on Piazza. One thing we're going to do is we're going to send out a survey after this homework, after everyone's submitted with this homework, to kind of get a sense of how much time people are spending on these homeworks, sort of how many hours, because the requirements for the course, I mean, it's supposed to be a 12-unit course for the 688, a 9-unit for 388, so it's supposed to be 9 hours or 6 hours of outside time per week. Having said that, it's also going to vary a lot depending on your background, right? Because it's 96 hours for CS as a CS course. So if you don't have that sort of some of the background, you'll need to spend more time. But having said that, we are trying to play this by ear as we go to see how much time people are spending on it. So the goal would be to hit approximately those marks on average for the people in CS, basically, for people with that kind of background. And if we are missing the mark by a lot, we can adjust the homeworks accordingly. But that is our goal, to hit those marks. Now, in terms of the actual deadlines, the one thing we may do, which I'm not certain yet we're going to do, because it actually shortens the time you have to evaluate them, is we may push the tutorial deadline back by 2 days just to give people a little bit more time to do it. But then you'd have a more crunch time in the evaluation phase. So you'd have to, grade other people's tutorials faster, but that's probably a little bit less work than writing it. So we might do that. That was the original day. Actually, we shifted it for that exact reason, to give people more time, but we might shift it back. And then in terms of the other things, though, I mean, we do, like the tutorial is due in a week where there's no homework due, so we try to shift it a little bit. The final project, of course, has no homework due that week. So we're trying to do a little bit of this anyway, but we will use the results of a survey we send out to try to adjust as we go. You know, as a first-time course, there's going to be some and as a course, it's a lot of different sort of backgrounds. There's going to be some variation here, but we're going to try to hit those marks.
Yeah, I think that is the situation is exacerbated by the fact that it's the first time on the course, so lots of like the homework, the upgrading mistake, the grader mistakes,
Yeah.
or like bugs and stuff like that that we ironed out.
Mm-hmm.
That's like causing a lot of time too.
Yep, it does. We know. Okay. So let's get to the topics here. So I actually reshuffled a little bit the topics today, and I think we will actually change the topic on Monday because we're going to need to make sure we cover naive Bayes for the next homework. I'm going to shift topics a little bit to make sure we cover that next time or the time after. But this is starting to be an enormous lecture, this set of slides at least, but I think it all makes sense to code together, so we're going to keep it in one big set of slides. But I've updated these slides, so now the slides on the website for the last lecture and this lecture point to this set of slides here. So last time we got through, we started talking about regularization, and regularization as a different way of constraining the complexity of our model in order to prevent overfitting. Right? That was what we got to last time. So we'll finish that up, and then we'll sort of take a step back a little bit and have to talk about more general nonlinear features. So I've been using so far the example of these polynomials as kind of our canonical example of a nonlinear feature you can use to get nonlinear classification out of a linear classifier. And I'm going to, in that section, describe a few more general ways of producing kind of generic nonlinear features. Actually, I'm just going to talk about two of them. I'm talking about polynomials in multiple variables. So far we've kind of talked about one variable that we take polynomials of. I'm going to talk about multivariate polynomials. And then I'll also talk about radial basis functions, which actually, in my opinion, are kind of the single most useful generic nonlinear feature. So I'll highly stress that these are incredibly useful, and the first algorithm you should try after linear regression should almost always be linear regression or a linear classifier with radial basis function features, because they're extremely easy to code, they're extremely easy to set up, and they tend to work very well. So I'll highlight what that is. And then I'll talk about nonlinear classification. So before we talked about regression in the nonlinear case, and I'll switch gears now to talk about classification in the nonlinear case. And really here, the nice thing here is that this is going to be exactly the same as our old classification setting, right? So the whole point of this framework for machine learning was that we could use the exact same algorithms essentially for regression as for classification. We just have a different loss function. And when we talk about nonlinear versus linear versions, all we do is we replace our features from being a purely linear set of features to a nonlinear set of features. So we kind of get nonlinear classification in some sense for free. We don't have to actually talk about new algorithms. We just add nonlinear features, and I'll illustrate what that looks like in the classification setting. And finally, I'll finish, hopefully today, but maybe next time, on methods for evaluating machine learning algorithms. So this is a little bit of a switch here, because so far we've been talking about running the machine learning algorithm, right? Sort of producing results. Some work on cross-validation and overfitting, but really it's just been about kind of our own analysis of how these things are working. I'm going to then switch gears to talk about how, if you want to, write a paper or write some report on your topic, how you should actually evaluate results in that context and how you should report your results there. So that'll be the last two elements. So let's jump right into regularization. When we ended last time, we were talking about regularization as a different way of preventing overfitting in our model. So instead of just minimizing the sum of losses, we minimize the sum of losses plus this regularization term here, which adds a penalty to the weights, to how big the weights are of our classifier or regressor, right? And the intuition here was, at least for polynomials, the way we would get these crazy functions, right, the way we get those things is exactly by using really large value weights, or really large coefficients for our polynomials, such that we kind of pass exactly through the data points with this very squiggly function that isn't actually going to generalize very well. And so we can prevent this from happening by constraining our degree of our polynomial, which we saw last time, or we can do it by forcing that the coefficients themselves have to be relatively small. And that's what regularization accomplishes. And by varying this from 0, meaning no regularization, to infinite, meaning you always pick the 0 parameters, you can kind of sweep out the whole curve of performance. So the figure actually looks exactly like this. This cartoon, at least, and I'll show the real thing in a second, looks exactly like the same thing we had as with model complexity in general. The only difference here is that for regularization, high model complexity means low regularization, right? It means low values of lambda, because that means that we can pick our parameters however we want to minimize our error, whereas low complexity means high values of lambda, right? Because that means that we are essentially choosing 0, or effectively 0, as our parameters. That's low model complexity. So let's see what this looks like for least squares. And I'll be pretty brief here because I don't want to get too involved in the derivations. We actually use the exact same rules as we did before. But it turns out there's a very nice formula for regularization in least squares estimation, the analytical solution to least squares. So the way we do this is we take our least squares objective, which is we're trying to minimize over theta, x theta, I'll write 1/2 here just to be precise, minus y plus lambda times the norm of theta squared, 2 norm of theta squared. And I can take gradients now. This one is the same as before. So remember, this gradient of our objective is equal to, this gradient, remember, was this term. It's this thing plus x transpose times this thing in the inside the norm here, x theta minus y. And this one actually is this should be an over 2 here. This one actually is even easier. We actually had, in our previous slide on linear regression, we had the exact rule of what the gradient of that thing is. The gradient of this thing is just lambda times theta. Right? So that's, if that isn't immediately obvious, you can go back and look at the slides on linear regression to make sure that those are the actual same exact formula we're using as before. But once we have this condition, or this gradient, we now want to set it equal to 0. Right? And we do this exactly like we did before. We move the terms that contain theta to the left side of this equation. So that will imply that x transpose x theta plus lambda theta is equal to x transpose y. And this term here can be also written as x transpose x plus lambda I. Remember, I is the identity, so I times any vector is just equal to that vector times all times theta equals x transpose y. And so the solution is just going to be this thing inverse times that thing, which is what's the equation there. Which nicely looks just like the normal equations we had before, just with this extra lambda I term there. And so actually you should typically do that for a number of reasons. At least add some lambda there. It also for those that sort of had asked for this before, it also happens to avoid things like this matrix being singular, being non-invertible. Adding that term always makes it invertible. And it just sort of conditions the problem nicer. But what you're really doing kind of effectively when you add a little bit of the identity there is you're regularizing, adding a little bit of regularization to your least squares problem. OK, so let's see what this looks like now. So I'm going to take my 20-degree polynomial. Actually, where did I? I thought I had another figure here, but maybe I didn't. Okay, I left this out. I'll put this in the slides again. But I had a figure on the what this actually looked like when you use a here's the 50-degree polynomial we have normally. Unfortunately, I can't really show this very easily. But if you take a 50-degree polynomial and add regularization, you actually get a version of this that looks essentially like you have for a lower degree polynomial. So even though it's a 50-degree polynomial, you actually will not overfit to this thing. You won't have those crazy lines there. You'll have a reasonable function. And apologies for not having that. I'll show it next time in class, or I'll just put it in the slides. What I do have is the plot of the actual errors you get for this over different values of lambda. So this is a plot now of different values of, and so you have to kind of use your imagination to see what these things might look like. But if you vary the regularization parameter lambda between essentially 0 here, this is basically 0 at numerical precision, and something very, very large. This is for a 50-degree polynomial now. So 50-degree polynomial is something that if we don't use regularization, clearly overfits the data very, very highly, right? We saw that before. You have 10 to the 7 is your error on the holdout set. Of course, your error in the training set is still very low, right? So this blue line here is still really low here. But your error on your validation set is incredibly high. So what I'm showing here now is the value of the average squared error on the training set and the holdout set for different values of lambda. So it's important to sort of see what's happening in this plot. First of all, these things are not smooth, right? So it's not like this is a nice smooth function here. It's actually going to have all these weird dips in it just out of kind of the fact that polynomials are irregular, and sometimes if you have a certain weight, you might get a certain shape polynomial that has errors some way versus the other way. But which I can't explain exactly why it's happening those dips right there. But what the main point to take away from this is that this is not a nicely smooth function with just one optimum. This is actually can be a nasty function here. But as we increase our regularization, what happens is we start to reach some area where we actually have fairly low loss, both on the holdout set and on the and on the training set, right? So in this region here, we actually seem to be doing pretty well. This is actually similar to how we performed when we used a reasonably low degree polynomial. We're just using now a 50-degree polynomial and regularizing it. All right, so this is sort of the nice region where our training loss and our testing loss, or sorry, our holdout loss, are both fairly low. We can kind of look at that a little bit closer. The next slide here, though I'll jump back to the other slide in a second. So this is now varying it between negative 10 to the negative 5 and 10 to the 3. And we have this sort of nice, fairly big region here, actually, where we get reasonable performance with a 50-degree polynomial, even though that seems like an absurdly large polynomial for this kind of data. The other thing that happens here is that once you get high enough regularization, you reach some steady state of your loss. And the reason for that is that, again, what's happening here with high enough regularization is you're effectively picking 0 for your parameters. You're picking theta equals 0, or theta equals something really close to 0. When you pick theta equals 0, you make predictions of all 0 on all your data points, right? That's just what you predict. You predict 0 for everything. And that gives you some loss. It's not infinite loss. It's just some finite loss, some squared error between it's actually just the sum of the average of the outputs squared is what it is, right? Because you're predicting 0, square that from the actual, and take the average there. So when you get theta too big, lambda too big, you hit some region where you're clearly just don't have any kind of interesting classifier to predict, but you still have some loss. So the idea of choosing a good lambda, just like we did for choosing polynomial degrees, is there's some kind of sweet spot where you want to choose lambda in this range, such that you actually get reasonable performance on both the training set and the holdout set. The question?
Yeah, so I'm assuming like you had like a small model and it chose lambdas across that scale and not.
Yeah, so what I'm doing here is I am taking this problem exactly, this problem. So I am taking all our days of data. I am taking a 50-degree polynomial. So my parameters here are 50, 51, I guess, because you have the constant term here. So 51 different theta values, and I'm finding those by forming my matrix of all our polynomial values, finding the least squares solution, and evaluating it both in the training set and the holdout set.
So when our data is too large to just run arbitrary computations and then compare them, how can we heuristically determine a good range?
I'll get to that in a second. Yeah. Yeah. I mean, we talked about this already a little bit. We talked about the holdout sets, right? So the idea was, or cross-validation. So the idea is you want to pick your theta such that it does well in both holdout and cross. And the way a common thing to do is basically because you have a relatively small number of hyperparameters, you just grid them or pick some sort of finite number of them and then choose the best one in your holdout set.
You tried on a subset of your data?
I mean, that's up to you. The question was, do you try it on a subset of your data? You can, sure. It's not a rule. I mean, that's just what you can do in the time you have available. Yeah.
So it seems like the regularization on one side it's lowering the variance, on the other side it's lowering the bias.
Mm-hmm.
So is it doing both? Or?
Yeah. So I haven't used the term. So the question was, it seems like it's lowering variance on one way and bias in the other way. Yes, it's certainly true. I haven't used the words variance, bias and variance here. Bias means your classifier is not rich enough to express the data. Variance means your classifier is making predictions that are kind of so noisy that they don't actually do well on a holdout set. So if you want to talk about bias and variance, just for those that sort of know it, this side here would be high bias because you have a model that cannot capture very rich features, right? It's basically predicting 0 all the time. And here you have high variance. In other words, it's hitting your data very well, but it isn't able to generalize very well because it's a very complex model you're using. So that's sort of the trade-off here. Is that this one's high variance. This is high bias here. Again, if those terms help you, that's great. If they don't worry. Okay, so now let me switch gears a little bit and be a little bit more general. I've been kind of very concrete so far in terms of talking about a specific class of these features. So, namely, polynomials in one dimension, right? Which is great, but they're kind of boring too, right? I mean, is that always what we want to pick for features? It seems like we have a lot more freedom than just to choose that. So let me talk about a few other classes of features you can use, one of which in particular I think is one of the more useful types of features you can use in practice. So for this section, and really for only this section, I'm going to use a little bit different notation here just to be a little bit more clear. So hopefully it's more clear. That's the goal at least. You can let me know if I succeed or not. So let's talk about a little bit more general sets of feature transformations we can do. And so for this lecture and this section, I'll switch back immediately. But everywhere before, I've been using xi to denote the input features, right? So xi's themselves contain both, say, the actual temperature, but also the features, the polynomial features in, say, the temperature, right? So that's what I'm using before. Here I'm going to switch to xi's, and really I'll even omit the superscript because it lets me write less. So x, in general, here is going to refer to the raw inputs. Where the raw inputs are just those things that you sort of are kind of the base underlying inputs to the features. So in the case of the temperature, the raw input would just be the temperature, and then the features would be all the polynomials we construct in that raw input. Does that make sense? I've used that term kind of informally before, but I want to make it a little bit more formal right now. And I'm going to call phi are my input features now. Those are input features. So this is the old x. And apologies for, I could use a different number or a different letter for the features themselves, but this is pretty common. And so I wanted to at least in one slide have this. It's very common to either write phi for the features or even phi of x, where phi is actually a function and x is the raw input you're applying that function to. And this is a feature mapping. But here I'll just think of this as a vector. I will assume that this x is a vector in Rk, where k is some number presumably less than n. Doesn't have to be, actually. You could have features that are smaller dimension than your input. But the underlying raw input is dimension k, and this one is going to be dimension n. Just the conventions I'm using here, not sort of general terms, and I'm going to abandon this now once I finish this one section. So hopefully that makes some sense. I'll try to reiterate that when I can. So for example, in our high temperature setting so far, our raw input, x, was just the high temperature. In fact, just that thing. It's not that in the constant term. It's just that thing, because that's the only actual input we have to our data. And so that's going to be, k is going to be equal to 1 in that case, right? If we make now a set of quadratic features, n would be equal to 3, because we have the squared term, the linear term, and the constant term, right? So just basic kind of definitions here, but that's the definitions that I'm going to be using. Okay, so how do we think about polynomial features? Let's take polynomials. How do we think about polynomials now of not just one input like I did here? That's pretty easy. You just take that term to many different powers. How would I think of polynomials in more features? So think about classification, or even the regression case where I had two features now, one which was the temperature, another one which was whether or not it was a weekday. How would I form polynomials in those two? Weekday is a little bit odd, though, because that's such a binary feature, so that's kind of special, but I'll mention that later. But if I have two other features, say I have high temperature and low temperature, how would I form polynomials over those variables? So one thing you can do is kind of maybe the most obvious thing, which is just form a polynomial in each one and then stack them together, right? So I just take my x1, so my features then become x1 to the d, x1 to the d minus 1, all the way up to x1 to the 0, actually sorry, to the 1, because the zeros will be all the same. They would each have their own 1. So just x to the or just xi, x1. All right, so I have that. That's my sort of features for my first variable. Then I do x2, similarly, x2 to the d, x2 d minus 1. And I keep doing this until I get to my xk to the d, and then xk to d minus 1. And then I finally pick 1. I realize that's very poorly written there. Xk to the d, down to xk, and then finally a 1 at the very bottom. So that could be my great big feature vector that I construct of all polynomials. The problem, though, this is not really a general polynomial in these variables. In particular, it does not have any cross terms, right? So it has terms like x1 up to degree d, but it never has a term like x1 times x2, right? So those terms are missing from this. And in fact, a lot of the nice features of polynomials, like their ability to express complex functions that can kind of go in, actually I don't know quite how formal I want to be here. But a lot of the nice features of polynomials don't hold if you just sort of use independent polynomials in each feature, or in each raw input, rather. So we want something a little bit richer than this. This is not a very rich representation. What it means essentially is that you have to have a separate polynomial in each dimension, but you can't, for example, capture correlated nonlinear functions of the different variables. Right? So a function like this, if I have x1 and x2, x2 and x1, a function like this couldn't be captured by these polynomial variables. All right, so let's look now at what actually the more general formulation is. So this is the actual formulation that we want. What we actually want to construct a feature vector of is the following. I'm just going to erase this because this is nothing you're going to use, so don't do this. I guess you could do this if you want this for some good reason, but in general, this is not sort of what people mean when they say multidimensional polynomials. What they mean is the following. And I'm going to use kind of set notation here, but to be clear, what I mean here is that phi is a vector that contains all those elements. So phi is going to be a vector that contains the following elements. The product from I equals 1 to k, k is the number of raw inputs, remember, of xi to the bi, where the sum from I equals 1 to k of all the bi terms is less than or equal to our maximum degree d. Does this make sense here? So I'm taking, conceptually at least, this makes perfect sense, right? How you actually implement this is a little trickier, but we'll show that in a second too. It's not that hard. What I'm saying here is that we have a product, our individual terms in the polynomial feature vector are going to each be a product of some of these xi terms, right? Where if, say, all the bi's were 0, then that product would just be 1, right? If b1 is equal to 1 and the rest are equal to 0, then this would just be x1, right? So by setting my b's, if I have, say, x1 to the b1, x2 times x2 to the b2, x3 to the b3, right? Say I just have these three terms. By making this one equal to 1, 0, 0, I would get just x1. So b1 equals 1, b2 equals 0, b3 equals 0. That would imply that this thing is equal just to x1. As you can see, these things just become the powers of the different terms in your polynomial here. And so by taking all the different possible combinations of powers, where the powers sum up to some number less than d, we get all the possible, each term is called a monomial, but we won't worry about that. But you get all the possible monomial terms that make up a general degree d polynomial. Yeah?
So this is the only the ith entry of the phi vector.
So the question was, this is the ith entry of the phi vector. No. So I here is enumerating over these things. I'm just saying that we take the set of all of these. Now, which one is the ith entry? It's actually not easy to say, because you have to ascribe some sort of ordering to how you choose these powers, right? You have to sort of pick, maybe you pick them all 0 first, then you add 1 to the last one. Do you then pick 2 on this one, or do you add 1 to here first? Right? You have to actually say what the ith element of this whole vector is. That requires you to specify some ordering for how you want to assign these things. All I'm saying here is this a vector that contains all of these. So every combination of bi's such that the sum is less than or equal to d, that is this vector here. I'm not saying what order the vector's in. I'm just saying the vector contains those elements. Right? Specifying the order actually is kind of annoying. It's kind of tricky if you want to do it without making the whole thing. But you can. It's just a little bit cumbersome. But let me actually show you an easy way to. So this is great. This is sort of nice math here. Conceptually, hopefully it's understandable what these things are. But it's a little bit far away from actual code, right? Because how do I enumerate the set of all b's such that this condition holds? It's actually not that trivial. I mean, I could count them, generate all of them. Say where each of these could be up to d, and then select only the ones where the sum was less than d. But I'm generating a lot of wasted effort there. So it's actually not that obvious to see how you would programmatically generate all possible polynomials. So I'm going to tell you now how you do that. Because it's conceptually very simple, but it just trips people up a lot. So I'm just going to give you the line of code that does this. So here's a line of code that does this. It uses some tricks in Python that kind of make life a little bit easier. So look at the first one. I'm going to use this function from the itertools library called combinations with replacement. And what that function does is it takes a list of elements, takes a list of elements, and selects, in this case, d of them. So it will select d of those elements where in a tuple. Where you can replace the things again. So essentially, if my first entry here is just conceptually a list which has x1, x2, and x3, then combinations with replacement would actually select all elements where I select x1 k time or x1 d times, x1 d minus 1 times, and x2 1 time, all possible combinations of those things. So then I take those tuples and I compute their product. And their product is going to be the actual set of polynomials of degree exactly d. Okay. So this is just a little, I mean, again, all I'm doing here actually is putting that equation into code using this very nice function that avoids you having to actually enumerate all possible powers here. You're just actually taking, a product using combinations. And then this one up here will generate only those polynomials of degree exactly d, because it always selects exactly d elements from this list here. If I want all the things with degree up to d, I just do a double loop here where I iterate I in the range of d plus 1. I want to have degree d exactly, so I use d plus 1. And then use the combinations of x with I different elements selected. By the way, this is actually a little shorthand here. You can do these nested lists here, where if you want one single list over two things, you can kind of nest the for case. You could have two for clauses here in a list comprehension. It's just a little trick. So this is one line of code to generate all the polynomials. I think if you do this yourself, just without knowing that, it can be a lot longer than that, the code here. So I would recommend just doing this. It's also pretty efficient. The last thing I'll say is it still takes some time. So if I have a whole data matrix, you could, for example, just call this function on each row of that matrix, but that would then be iterating over a lot of these things, calling this function a lot of times. So actually, here's the one line, though it breaks over multiple lines in my slide here. Here's the actual one line of code you can run to generate all polynomial features up to degree d from an entire data matrix with one call. And all it does is it just makes that call over the columns and then multiplies each column separately. So you basically are grouping this thing by columns and then forming individual polynomials on the columns. Again, that's getting kind of complex, that Python code at that level, where I'm using a reduce call and multiplying things in a list together. But this is where Python starts to get nice too, is you can generate all polynomials for a data matrix by making that one call. And the reason why I'm saying this here is that tools like scikit-learn, they don't actually do this that nicely for you. They have some tools like this, but it is just one line of code, so you can just do it. But I wouldn't expect you to come up with this line of code. It takes a little bit of thinking to come up with it, and Stack Overflow queries. Okay, any questions there? This line is meant to be kind of copied directly into your notebooks if you want to use those. Yeah. Yes. Okay. Actually, that's a great point. I didn't actually. All right. Let's talk. Well, I talk about this in a second, but let me mention it now. This feature vector here, the number of and this actually is not. This is not obvious, by the way. I'm just telling you what it is. It's going to be k plus d. Choose k. Actually, also the same as choose d, but choose k. Right? Which is a really big number. Right? K plus d. Choose k of those elements. If either k or d is at all big, you're talking about a whole lot. This grows exponentially in either one, given the other one being fixed. So this is a really big number, and very quickly becomes impractical, which makes perfect sense, right? Because if you have 100 features, and I'm talking about a polynomial over all those features that is not, of degree 5, that's not something that you can easily enumerate, right? I mean, you can just think about how many different possible monomial terms there are. There's a lot of them, right? So I'll talk later, a few slides from now, about how to actually make these things practical. And with polynomials, it's actually hard. It's not that obvious how to make them practical, actually, because you can't get around the fact that when you have polynomials, you would have a lot of terms. So you have to typically use some level of sort of, probably drew on myself there. You have to use some level of sort of insight into the problem itself in order to determine which features you want and which you don't want. Yes, so this is a generic function. If you run this function on an array of even moderate size, it will run out of memory. So It's great, you can do it in one call, but it will never finish for in a lot of cases. Yeah, they're very, very big, those feature vectors. Okay, so let's talk about, that was sort of the general case of polynomials. Let's talk about one more type of feature vector, which I think is actually one of the most useful in practice. And again, this being a practical data science course, I would actually say this is probably the single most important generic nonlinear feature you should be familiar with. And these are called radial basis functions, or just RBFs for short. So an RBF is a feature of the following type. We pick, and I won't say yet how we pick these, but we pick somehow, I'll probably get rid of this. We pick somehow a set of centers, which I'm going to denote mu1 through mu1 through mu p. And these are all vectors in Rk. That's the space of the underlying raw inputs. And an RBF feature is just an exponential of the negative square distance between those means and the data point itself. So written kind of similarly as we did above, the set of features for a vector x is going to be equal to the set of all this quantity, negative x minus mu I. Of course, if you have all your features here, you need to also iterate over all your features. I'm showing this for a single x, so assuming a single input. This is how you generate the RBFs. 2 norms squared. This is the distance between essentially x and mu and the Euclidean norm, divided by 2 sigma squared. And this is done for all I equals 1 to p. And I also actually said even that we're going to add the constant feature too. That's kind of optional. Just in the polynomials, they have the constant feature, so I added it, but here I'll just add it explicitly, because no term here will actually be equal always to 1. Okay, so does this actually kind of make sense a little bit of what's happening? I'll draw a little picture of this. But I want to explain while I draw it, so I'm only going to draw it on the board. I don't have this in the slides. So if I have my, say, one-dimensional feature with the value x there, right? What this says is I also, on the same axis here, put down a few mu's. So I have mu1 here, mu2, superscript 2. And here I have mu3, say. And I'm not specifying how I pick these yet, nor am I specifying how I pick sigma. So I've left that up to sort of choice for now. But around each of these, you can think of this function as looking like a bell curve with maximum value 1. So that's what the negative exponential squared is, right? When this thing is 0, this whole term will be equal to, the exponential of this whole term will be equal to 1. After that, it'll tail off very quickly. So you have these sort of functions that look like this. This one maybe looks like this. This one looks like this. Right? So that's what these should all be the same height here, at all equal to 1. This is equal to 1. And the feature vector then just becomes the value of these bell curve looking shapes at the point x. So the feature vector becomes, this point here, this is this one, this point here, this value here, this value here. That would be the feature vector. Right? And what this kind of captures is these functions capture locally smooth, kind of a locally smooth basis, right? Because the feature vectors here and very close by are going to be very similar. Similarly, if for all the means that are very far away from this point, those features are going to be essentially 0 So they don't actually play much role in what the feature vector is. The only feature vectors that actually play a role in kind of saying what the value is here are the means that are close to this function. So it turns out that when you use these functions, you can represent smooth functions, kind of locally smooth functions over your raw input space. But they can be nonlinear and locally smooth, and we'll see a few examples of that in a second. All right, any questions there? Because this is actually tricky, but it's also one of the most useful things, so I do want to spend a little time on this. Yeah? Sorry, what was that? Okay, go over the graph again. Okay, so what I'm showing in this graph here is I'm showing a single input. So this will be the case of k equals 1. In other words, we have a single raw input. Okay, and I've also shown 3 different means that I have here. So I've picked somehow 3 different mu terms that each correspond to some value on this same input space. Okay, what I'm drawing now is in these, and this is sort of an odd figure, so I will spend some time on it, so please ask questions about this. What I'm showing here is I'm showing the value of this function as a function of x. So I should, this is my actual input x, but I'm showing now as a value of x varying over this whole axis. So as a value of like x1, right? And so this expression here for mu1 would sweep out this shape. It's this bell curve shape, where its maximum is at 1, and it has that value. That is the value of this expression for different values of x. This one is the value of that expression for different values of x as well. It's a different function because the mean is different. And this one is the value of x for this one. Sorry, the value of that function for these values of x, right? What our features are is our features are the function values for all these different functions implied by different centers, all just concatenated together. So that becomes my feature value. The feature value just becomes all my set of these expressions. Phi is all of these things. So phi would be for this value of x. Phi would be this value, or really this one first. So it would be this one, and this one. That actual numerical value of this term, where you evaluate it once with mu1, once with mu2, and once with mu3. That's what phi is. Now the reason you might do that is that these types, and again, this is something you have to kind of just explore a little bit and see, but these features can encode functions that are smooth in the input space. So if I take, if I use linear regression now, what I am doing actually is I am encoding essentially some linear combination of these 3 functions, and that linear combination there, the sum of these 3 functions with some coefficients on them, and that function itself has to be smooth because each one is smooth, but it can be nonlinear, right? So like this one minus this one plus that one, that would be some interesting nonlinear function in our input, but it's smooth because each term is smooth. Yes.
So when we have an x, and for each x we have, if we have 3 means, let's say in this example, 3 values for each of the means, we have, so for each x we will have 3 predictions.
No, they aren't. So the question was for each x you have 3 predictions. They aren't predictions. They are features. So just like a polynomial, x squared was not a prediction. X was not a prediction. You take those terms and you add them together with some coefficients. Phi is the feature vector that we're going to eventually, hit with theta to form our actual hypothesis.
So from let's say a vector of raw features, we get a matrix of.
No, it's not a matrix because a vector of raw features. So I'm showing the case of k equals 1 here. For k equals 2. This is still just a vector of features, right? Because you take the Euclidean norm here. So if you're in 2D space now, and I guess I can draw the figure in 2D too. So suppose you're in 2D space now, x1. My data point here is x, right? So this is x, and these are this is mu1, this is mu2, and this is mu3, right? And so our values would be the two-dimensional bell curve around these things. They look like this, kind of. So the value here would be the first feature. Well, actually, the value here of this one would be the first feature. The value here would be the second feature, etc. Okay? But each value here, each of these numbers, each of these expressions here, whether x is a vector or a scalar, is still just a single real valued number that you compute for each different center. So here phi is going to be a vector, just this one, I guess. I'll ignore the constant term. This is going to be a vector in r to the p, right? No matter what. Whatever the size of the input is, it's going to be a vector in rp.
For the single raw input feature, we get the three values, and then we take the norm, which creates a single real value, and eventually we have that single feature value for each single raw input, right?
I'm not quite sure. So I think what you're describing is correct, but it's actually, I see it as simpler than that. This is a function that takes as input x, outputs a real number. Yeah. The features are just all of those real numbers, evaluated once for each value of the centers. Now I have not said how to pick the centers yet, or how you pick the sigma parameter, which is called the bandwidth parameter. Those you can think of as hyperparameters. The same way you had hyperparameters like the degree of the function, the choice of your centers and the choice of your bandwidth are also hyperparameters. Seem like very big hyperparameters, I know, but they are hyperparameters, in fact. So we'll talk about how you pick them in a second. But that's how you that's a radial basis function. Yeah.
Could you also have the same center with different sigmas?
So question was, can you have the same center with different sigmas? You can, but I'm not going to write it that way. I mean, you can't in this formulation, right? Because this formulation, they all have there's only one sigma, and there are many centers. You could have each center have their own, its own sigma, in which case, yes, you could have two centers with different sigmas for that, and those would be two different features. I would recommend against doing that, though, actually, for a reason I'll talk about in a second. So, okay, yeah. Yeah, so I haven't talked about sigma yet at all. Sigma is a bandwidth parameter. And the way you can think about sigma is, for those that are familiar, and again, you don't have to be familiar with this to know this. I'll describe kind of what this actually means in a second. But sigma is a bandwidth parameter that acts kind of like a variance parameter. For those that know about Gaussian distributions, it acts actually very much like a variance parameter. The idea here is that very small sigma, so if this thing is really small, right, then this term is going to be, if this is very small, then that will make this inside term big, even when the distance is relatively close, right? So if sigma is small, this term inside the exponential gets very largely negative for even points that vary a little bit from their center, right? So basically, what it looks like is that small sigma, so I have my axis here, I have my mu, and I have x. My function would be something like this. For small sigma, I get things that tail off very quickly, right? Whereas for large sigma, I get things that tail off much more gradually. Importantly, unlike a Gaussian distribution, again, this is just for those that know, we'll talk about those next time, but unlike that, there's no normalization on this, so the max here is the same in both cases. The max is always just 1 in both cases. But the thing with sigma is going to be a lot, with low sigma, it's going to be a lot narrower. So you can think of, and the reason we use sigma there, in fact, in that notation, is exactly because people are familiar with Gaussian standard deviations. And so it acts like a standard deviation term in a Gaussian. But it's not, actually. It's just a functional form. And so it just acts like that. We could just as easily take that out and put it in front, right? Make this like the exponential of gamma times that distance, where gamma is equal to 1 over 2 sigma squared. But people don't do that just because a sigma is kind of a way people are familiar with standard deviations in Gaussians, and so we use sigma the same form. Okay. So now how do we pick the centers, and how do I pick the bandwidth, sigma? Actually, first I'll give an example. I already gave an example for this, but for example, if I have high temperature, I could pick, that's my input variable. I could pick means, which are 20, 25, say evenly spaced to 95. I could pick the bandwidth to be 10, say, and then on each of these things, what they are is they're the exponential of the negative high temperature minus 20, all the way up to the minus 95, divided in all cases by 200. So that would be a set of RBF, radial basis function features, based upon the raw input of the high temperature. Okay, so now two important things here. When you compute radial basis functions, you have to normalize your data first. And in particular, if you have, let me just go actually to our next example. So we're going to talk about classification in a second. This was our classification example where one axis was mean number of pixels of the area of the cell, and one axis was the number of concave points. So if you compute distances in that raw space, right, the distance in that dimension will be completely dwarfed by the distance in this dimension, right? Because the distances, these are in units of thousands. These are in units of 0.1s. And so in order to actually have reasonable radial basis functions over that space, if you're going to constrain us to have one sigma, I mean, you can also constrain the sigmas to be different, but if I'm going to say, or actually no, you couldn't even do that, sorry. You'd have to have like a different norm here that had different scaling of the different terms in the norm. So we're not going to worry about that. All I'm going to say is before you apply a radial basis function, make sure to normalize your data. The most common thing is either the thing I mentioned a couple lectures ago of making your data mean 0 and standard deviation 1, or make it have a max of -1 and a max of 1 and a min of -1, like I did for polynomials, right? So you can scale it either way, either by constraining the max and the min to be a certain thing, or constraining the standard deviation and mean to be a certain thing. Doesn't really matter which of those two you do in this case, but just make sure that your features are all on the same scale. It's very important for constructing radial basis functions. So that's the first thing. Second thing is, how do we pick the centers and the bandwidth? I didn't say that at all yet. So the obvious thing to do for centers, right, would be to pick them in, say, a uniform grid over the space, right? So, if I have a one dimension, it's sort of easy. I just take maybe my minimum max, and I just space centers uniformly in that range. If I have two dimensions, let's do the same thing. I just now make it a uniform grid in 2 dimensions over the points. Now, as you may be guessing, that sounds great. That seems reasonable for 2 dimensions. We're going to quickly have the same problem we have with polynomials, right? Where for high dimensions, we're going to talk about having a regular grid over k different dimensions. The number of centers, if I do that, will grow exponentially in the dimensions. That seems like a problem. So we'll get to that in a second. Before I do, here's the code, by the way, to compute RBFs. You can use a few more tricks here as well. This is given a whole data matrix X. This is, every row of this data matrix is a example, and every row of the variable mu is a center. This computes all the features efficiently. So this basically gives you start with a an M by K matrix that contains your raw features. You have a set of means mu to the, it should be P there. Let me fix that. Mu is P by K. And what I do here is I basically construct all those things, again, kind of using a trick that makes the thing more efficient. So what I'm doing here, for those that care, is the hard part of computing radial basis function features is you have to compute all these distances, right? So I have to compute a matrix of all pairwise distances between every mu and every x. I could do that by just looping over all mu and all x. That's not that efficient. It's much more efficient to use matrix operations to do this. Actually, maybe I won't even, well, I'll just say it here. So if I have something like x minus y squared, this is equal to x minus y transpose x minus y, which is equal to x transpose x minus 2x transpose y plus y transpose y. And what I'm doing here, and this term, if x is one of the rows of the big matrix X and Y are the means, that's an individual term of a big matrix product. So I'm forming a matrix product. And for these terms, I'm also actually adding this term to all the rows and this term to all the columns. So that's just sort of the notation we use for doing that. Again, much nicer than sort of doing a for loop here. It'll be much faster in Python. So this is how you compute. And I'm getting you this again because you should use this for your homework. I think the 688 version is going to have RBFs. You should use that. Don't try to do them yourself, and don't try to do it with a for loop because it'll just be very slow. OK, moving right along. So we're definitely not going to get to the evaluation this time, but we'll see how far we get. So the problem with all these things, actually, are there any questions before I move on? I know there probably are. Yeah.
So can you go back to that 2D space?
Yeah.
So since like RBF is for getting nonlinear features
Mm-hmm.
classification, do we think about like those P centers as like P classes, and you're trying to find out how far you are from P?
Don't think about it like that. Classification, classes is a very bad term here because classes implies something about the character of these points. They are just centers, and they're just points in space. And think actually instead about the functions that sort of surround these things. Your final classification, our final hypothesis function is going to be a linear combination of those functions, right? Because essentially what you're doing when I specify my, my final form is I'm taking some linear combination of my parameters. I mean, I take an inner product of my parameters and the feature vector, right? So that will be some linear combination of those things. So my final functional form is actually going to be a sum of these different functions there. Now, what those classes are, where in that space, doesn't actually matter at all. We don't know anything about that. What class they are, we don't know anything like that. All we know is we're just picking some points, say in a uniform grid, and then we're putting these little functions around them.
But the phi matrix or vector kind of indicates how far a point is, right?
Yeah, exactly. So for a given point x, the phi vector for that point x indicates how, well, not really how far, but it's the exponential of the negative of how far you are from those points. Yeah. All right. But again, when it comes down to it, all we're doing is doing some feature transformation, right? We're just taking inputs and producing something else, which is a nonlinear function of those raw inputs. And I'll show you what they look like in a second. OK, so before I do that, though, I should mention that these things, as I've described them so far, are not very practical, either polynomials or radial basis functions. So polynomials are not practical because there are a lot of them. And RBFs have the same problem, actually. If I put a uniform grid around this space and have a uniform grid of centers, that can compute nicely kind of any function over that raw input. But I need, if I have an evenly spaced number of d, so if I have d centers along each dimension, then I'll have d to the k total centers, right? And that would not be very practical. So let's talk about how to make these practical. For polynomials, in general, don't form too many higher order polynomials of different features. Chances are they're not going to be that useful because there oftentimes is not any real meaning to things like high temperature squared times humidity or something like this, right? It's just, they aren't things that have any real inherent meaning, and so they typically, your function actually won't be a function of these things. The exception might be things like physics, where if you know that some underlying laws are actually polynomials, they can be great. But barring that, oftentimes you do not have polynomial relationships between your prediction, your output that there really is, and your variables. So if you want to use polynomials, you actually can do that first thing we did, which is independent polynomials in each variable. It's actually not a bad idea. You can also do things like only multiply certain variables together. And there are additional tricks, like if you have a binary variable, well, a 0 or a 1 squared is still the same thing as it was before. So don't take polynomials of the binary variables. So you can do all sorts of things. So you could have a polynomial of the binary variable times temperature. That would be a great one. But temperature times weekday squared, whether it's a weekday or not, squared. This is a weekday. Here is a flag, a 0 or 1, indicating if it's a weekday or not. Don't do that. Don't have the weekday squared anywhere in your feature vector. Now, constructing good polynomial features, the reality is it probably takes a little bit of insight into your problem, right? If you have, say, as I mentioned before, like a physically based problem, then they can be very good. But you probably have to have some insight into the underlying laws that are governing your data, so that you know what actual polynomial features might be good to include or not. You typically cannot just kind of blindly throw in a big feature vector or big input vector into your polynomial feature function, because it will lead to just way too many things. Now, radial basis functions are actually much more fun to make practical. And this is honestly the second algorithm you should try. You should first try linear regression or linear classification. After that, you should try this. Before you do a kernel, before you do gradient boosting, before you do a neural network, do this. All right? So here's the idea. First of all, do not create RBF centers over all the input in the data set, or over all the dimensions. Instead, create your centers to be some random subset of your actual input points. Or if you want to be a little fancier, and we'll talk about this later, use something like k-means to cluster your data, and then pick the means from k-means. Again, don't worry about that. We'll talk about that in a second. As your centers. Okay, that's point 1. All right, so do that. Now all of a sudden, p is very tractable, right? P is not that big. P is not exponential. It's just some fixed size subset of your data, or some fixed subset of output of the k-means algorithm. So use that to get the centers. And by the way, a random subset is probably fine. Works pretty well. Secondly, your bandwidth parameter. Do not pick it with cross-validation. Pick it based upon this. This is called the median trick. I have no idea where it actually came from. It's this sort of folklore in machine learning. It's this folklore in machine learning that everyone knows, but it's not written down anywhere as far as I can tell. So all these papers say we use the median trick to pick our bandwidth, and I don't know where it's actually written down. This is what you should do. Enumerate all the differences between your means, just the 2 norm, not squared, just the 2 norm, and then take the median of all of those. That's your bandwidth. There's theoretical reason why this is a good idea. It captures something about the actual likely spread of your data, but really it's kind of a trick that tends to work really well in practice. It almost always is the right value, or almost the right value. Certainly the right order of magnitude here. It's called the median trick. But again, there's so few references to it, and everyone uses cross-validation for this. Don't do that. Just use this. Okay, and with these two things, this is probably the single best, after linear regression, this is the next best thing to try on any data set. It works incredibly well. So I'm going to show this in the case, actually, I could show it in the case of our regression problems. I'm not going to. We're already kind of getting a little behind on this. I'm instead going to show all of these things in the case of classification. Right? So I'm actually going to spend very little time here sort of talking about the theory, because classification is exactly the same as we were doing before. Like linear regression, we really have the exact same algorithm for classification. When we move to the nonlinear case, we just use now nonlinear variables or nonlinear functions in our inputs for our inputs. I'm back now, by the way, to talking about xi's as our fees there. So apologies for that deviation in that one section, but hopefully it was somewhat intelligible. The only difference here is that instead of those x's being some linear, just our high temperature and whatever else, or I guess sorry, I'm back to the cancer data set. So instead of those x's just being the mean area and the number of concave points, it's some nonlinear features in those two raw inputs. All right. So and then after that, we just minimize our same support vector machine, logistical regression, whatever we want to do. We can just optimize that same function with, say, gradient descent. Okay, so let's see what this looks like. So I'm going to show for this task, I'm going to show when we train a linear classifier to classify these points, what does the resulting decision function look like? So again, what's really happening in this case is that we have our hypothesis class is a plane that comes out of the board, and it's positive everywhere that this is red and negative everywhere it's blue. And for a linear function, that was nice because I could actually plot the exact line where it intersected with the 0 plane, and that was our decision boundary. In the case of now higher degree nonlinear features, you oftentimes cannot get a closed form expression for this boundary anymore. But I still can plot what these things look like by essentially sampling a bunch of points. So I'm just sampling a whole lot of points down here across this whole space and seeing if they are classified as being positive or negative. Again, this is now a degree 2 polynomial. So the picture to have in mind is actually some second degree function. That would actually be a quadratic function here that kind of comes out of the board that at this level is negative. It's beyond the plane of the screen, and at this level is positive. So it looks like this sort of cone that's coming out of the board, and that's what these functions actually are. Remember, they're not. I'm not providing like a functional form of this line somehow. What I'm doing is I'm plotting the positive area and the negative area. Right? And just like for the case of high temperature, we can kind of go through what these things look like for different degrees. So if I have a third degree polynomial, again, this is actually the full third degree polynomial. It's not that hard to do because there's only 2 features here. It looks like this. For degree 10, it looks like this, etc. Now, also not quite as apparent because actually they get to be a lot really big. So it's actually you have to run a whole lot of these before you find real overfitting, or before you can sort of really see the same kind of squiggliness as you had before. We are still overfitting here, right? Because this whole area up there is being classified as negative, probably for no real good reason. And more than that, actually, for high degree polynomials, it usually winds up the case that this is not just negative up there, but it's very negative up there because they sort of go off, pick a very steep value. We have big values of our coefficients, and so in order to make sure that space there is negative, it actually takes on very low values. So not only are we saying that that's negative up there, we're saying we're very confident that it's negative too, which is probably a bad idea here. You probably aren't. It probably is not actually negative up there. There's no reason to think the function looks like that. So you might not want to use polynomials in this, or it might, for the same reason as with regression, you might not want to use polynomials of very high degree. Let's look just briefly at the RBFs now. They actually will look very, very similar. So here what I'm doing is, first of all, I've normalized my features to be between -1 and 1, so that our axes are kind of similar. I then I'm going to also now look at how these functions change, or how these sort of decision boundaries change as a function of the number of RBFs that we choose, as a function of the bandwidth that we choose, and then I'm going to show you what happens if we just do the tricks that I said and what that function looks like. So here, these 3 figures, I have 3 figures right here. This is 1, 2, and then 3. And what I'm showing in these 3 figures, maybe I should actually put them all on the same slide, but oh well, you can look through them you can download them and look through them. What I'm showing here is different D variables, and here D, I'm assuming that there's going to be D I'm having a uniform grid of size d by d over this two-dimensional space. So there's actually going to be p is going to be d squared here. There's going to be d squared total centers for our radial basis functions, and I'm picking my bandwidth to always be 2 over d. So basically, our bandwidth is just will get smaller as we have more and more centers there, right? Because you have more and more centers to sort of describe your data, so you make your bandwidth smaller so that each one can be kind of a steeper function or a less steep function. And what you see is kind of exactly what you expect, right? As you increase the number of centers, you can capture more and more complex functions over this input. So here finally is the d equals 21, and we can do things like have a little region here that has 4 positive points, only 1 negative point. So it makes this whole region here positive, whereas it leaves these regions here to be negative. So it's sort of fitting the exact values that we see here, and doing it in a way that kind of captures the exact classes of these samples. Now, as you might imagine, of course we are overfitting here, right? So if we evaluate this on a holdout set, if we left out that example, we would not classify the example probably as being positive there, so we would make an error on it in the other case. Whereas a boundary like this seems much nicer, right? It seems like we're much less likely to make a mistake when we have a boundary like this. So that is sort of, again, one way in which you kind of think of radial basis functions as capturing a similar kind of overfitting or underfitting properties as for polynomials. They can represent these sort of very complex nonlinear functions over the state space, but they do so in a way that, just like polynomials, can also overfit. A few more slides here. I'll just highlight them quickly right now. I don't want to spend too much time. I'll go through them again next time in class as well. The idea being that you can also control the complexity of these radial basis functions by increasing the bandwidth. So the bandwidth also acts as a model complexity term, namely higher bandwidths mean that the features are more constant across different values here. So if I had the extreme of a bandwidth being infinite, they're all equal to 1, so I have a very boring function. But as I raise my bandwidth, I actually get smoother and smoother functions. So this is still 20 features in each dimension, but here's the bandwidth 0.1, here's bandwidth 0.5, and here's bandwidth 0.7, which is what you get out of the median trick. So these things actually work pretty well. And then here, by the way, is the one if you just get the RBS from data, only 50 points, and use the median trick. This is actually a pretty nice function. Unlike, I should say, the polynomials, the values here, they are classifying as negative, but it actually ends up being a very sort of close to 0 negative value, because there isn't really any functions here. So these end up being basically close to 0. And you have sort of very nice, smooth, but this looks pretty reasonable, right? You kind of are getting the right shape here. You have these sort of nice forms of how these things look. That seems like a pretty reasonable version of this function, given the data we have available. So this is the second thing to try, always, after you try linear regression. Try this next. All right, so next we're going to talk about evaluating machine learning algorithms, and we'll move from there to probability next time. Okay.